Look up at the night sky. What do you see? Vast, dark emptiness sprinkled with stars. For centuries, we humans have thought of space as just that, an enormous vacant stage where the cosmic drama unfolds. The vacuum of space, a perfect nothingness. It's an idea that feels intuitive, simple even. We open a jar, pump out the air, and call it a vacuum. So space, devoid of air, devoid of everything, must be the ultimate vacuum, right? This common perception paints space as a passive backdrop, a silent, empty void between the celestial bodies that truly matter. But the universe, as we've learned, is rarely that simple. It loves to surprise us. Physicists, however, have a rather different view of this nothingness. Dive down to the quantum realm, the very fabric of reality, and the picture changes dramatically. What we call a vacuum is in fact a seething, bubbling cauldron of activity. Particles wink in and out of existence, a fleeting dance of matter and antimatter, borrowing energy from the void itself for impossibly short moments. This is the quantum foam, a concept that shatters the illusion of a truly empty space. It tells us that even in the deepest intergalactic voids, there's an inherent restlessness, a fundamental energy that a true classical nothing would not possess. Space is alive in its own way, even when it appears utterly desolate. This underlying quantum fizz means that even the emptiest patches of the cosmos have properties. They have rules. They can be bent and warped by gravity, as Einstein so brilliantly showed us. Light travels through this vacuum at a constant, unbreakable speed limit, or so we've traditionally thought. These are not characteristics of nothing, they are characteristics of something. Space, then, isn't merely an absence. It's a physical entity, a medium, perhaps the most fundamental medium of all. It's the stage, yes, but it's also an active participant in the universe's grand play, influencing everything that happens within it. So, if space isn't truly empty, what else could it be hiding? What if its structure is far more complex, more intricate than we've ever imagined? The idea of a simple void gives way to a landscape of unseen fields and potential energies. We've peeled back one layer of understanding, from apparent emptiness to quantum effervescence. But perhaps there are more layers still, deeper structures that govern not only how particles move, but how information, energy, and even consciousness might interact with the cosmos. This sets the stage for a new way of thinking about the very fabric of reality, a journey into the heart of the vacuum itself. Enter the Higgs field. You might have heard of it, perhaps in connection with the Higgs boson, the God particle. Its discovery was a monumental achievement, confirming a crucial piece of our standard model of particle physics. The Higgs field is often described as an invisible energy field that permeates the entire universe. Think of it like cosmic molasses, though that's not quite the full picture. It's everywhere, an omnipresent aspect of space itself. It's not something in space, it's a property of space. Its existence fundamentally changed our understanding of the vacuum, transforming it from a passive void into an active player. The most famous role of the Higgs field is giving mass to fundamental particles. Imagine particles moving through this field. Some, like photons, don't interact with it at all, and so they remain massless, zipping along at the speed of light. Others, like electrons and quarks, interact with the Higgs field, and this interaction is what we perceive as their mass. It's like wading through water. The more you resist the water, the heavier you feel, the harder it is to accelerate. This interaction is constant, a fundamental drag that shapes the nature of matter as we know it, determining how atoms form and how galaxies hold together. But the Higgs field is more than just a mass-bestowing mechanism. It defines a fundamental state of the vacuum. The value of the Higgs field is not zero. It has a background level, a non-zero vacuum expectation value. This is profound. It means that empty space has an inherent energy, a baseline characteristic due to this field. This Higgs vacuum is the ground state of our universe, the lowest energy level possible under current conditions. It's a specific configuration of space-time, not just an absence of stuff. This challenges us to see space not as a featureless expanse, but as a structured, energetic medium. This special role of the Higgs field in defining the vacuum is crucial. It suggests that the vacuum isn't monolithic. If the Higgs field can have a certain value, could there be other states, other configurations of space? If it provides a kind of resistance or interaction, could that interaction change under extreme conditions? This is where things get really interesting. The Higgs field, by being so fundamental to the nature of space, becomes a gateway to understanding deeper properties of the vacuum itself, perhaps leading us to structures and phenomena we've only dreamed of, like the layers of an accordion. This brings us to a fascinating idea, the accordional space field theory. It proposes that the vacuum of space, the very stage of the cosmos, isn't uniform or simply filled with quantum foam and the Higgs field in a flat way. Instead, imagine it as being layered, folded in upon itself, much like the bellows of an accordion. These aren't physical sheets you could touch, but rather different energetic states or densities of space-time itself. Each fold represents a distinct layer, a different potential for interaction, a unique way space can express its properties. This moves beyond just a lumpy vacuum to one with discrete, accessible strata. Think of these accordion folds. When the accordion is compressed, the folds are close, compact. When it's expanded, they stretch out. The accordional space field theory suggests that our everyday experience of space occurs on one surface of these folds. But deeper within, or perhaps between these folds, lie other states of space-time. Each layer, each fold could act as a kind of gateway, a transition point to a different mode of being for space. These layers are not separate dimensions in the way we usually think of them, but rather different intensities or configurations of the fundamental fields that make up space, including the Higgs field. These layers, these folds in the cosmic accordion, are not just passive structures. The theory suggests they are imbued with information and energy. Space, in this view, becomes a kind of living memory, a dynamic repository. Each stratum could hold echoes of past cosmic events or contain latent energy that could be tapped. Imagine information not just traveling through space, but being imprinted within its very fabric, stored in these different layers. This turns space from a mere container into an active participant in the storage and flow of cosmic data, a vast energetic library holding the universe's secrets. How are these layers connected? They are all part of the same fundamental space-time, just expressed differently. Movement through our familiar three-dimensional space is like skating on the outermost layer of this cosmic accordion. But what if we could learn to navigate the folds themselves? What if we could find a way to gently part them, to slip from one layer to another? This wouldn't be about tearing a hole in space-time, but about transitioning smoothly between its inherent energetic states. The connections between these layers are governed by fundamental physics, perhaps linked to the behavior of the Higgs field at extreme energy densities or under specific conditions. So what happens when something, say a starship engineered for such a purpose, moves very, very fast, or interacts with space in a radically new way? In our current understanding, as an object approaches the speed of light, its mass appears to increase infinitely, requiring infinite energy to go faster. This is the light barrier, a seemingly absolute cosmic speed limit. But this assumes travel through space as we conventionally understand it. The accordional space field theory proposes a different approach, not breaking the local speed limit, but changing the local space itself by interacting with its deeper folded structure. The key might lie at what we could call the Higgs threshold. As a vessel designed to interact with these deeper layers approaches this threshold, perhaps through immense energy concentration or a specific resonance with the vacuum field, the way it interacts with the Higgs field, and thus with space, could dramatically change. Instead of resistance increasing, what if it effectively flips? Or more accurately, what if the ship transitions to a layer of space-time where the effective speed limit is vastly different, or where the concept of distance itself is altered? The accordion folds offer pathways where the usual rules of resistance no longer strictly apply in the same way. Imagine your starship, now not battling the increasingly dense molasses of the Higgs field, but instead gently coaxing open a fold in the cosmic accordion. It slips into a corridor, a pathway through a different stratum of space-time. Travel through this accordion corridor wouldn't feel like a violent acceleration against crushing G-forces. Instead, it might be remarkably smooth, a serene glide. The universe outside your viewport might appear to contract or shift in unimaginable ways, as distances are traversed not by brute force speed, but by navigating these pre-existing, subtle pathways within the fabric of reality itself. You'd be moving with space, not against it. The implications of such a view of space are frankly staggering. It opens up the possibility of true interstellar travel, not in generations, but perhaps in manageable timescales. It suggests new ways to understand and potentially harness vast cosmic energies stored within the vacuum's layers. Beyond travel, it offers a profound new perspective on the universe. Space is not a static void, but a dynamic, structured, and information-rich medium. Unveiling the secrets of this accordional space and its connection to fundamental fields like the Higgs could be the next great leap for science, transforming our relationship with the cosmos from distant observers to active participants in its unfolding wonders.